Dr. Glenn Liston from the Air Force Scientific Research Laboratory will take us further into the regime of hypersonics.
Thank you, Dr. Abramson. When Dr. Mark first asked me to come out and talk to this group, I immediately had a question that came in my mind, because I thought this is the first time, quite possibly, that I'll be able to ask the audience a question and get a pretty significant positive response. So I'd like a show of hands. How many people in this room have flown at hypersonic speeds? I knew there'd be some. I knew it. And I wanted to talk about that because it's a relatively extraordinary thing, but the Air Force is counting on it becoming more common. Not necessarily for individuals to go fly at hypersonic speed, but to really take advantage of it for military applications. Let me see if I can figure out my buttons and not screw things up here. So, building upon what Rodney talked about, I'd like to talk about what is hypersonic and what is not hypersonic. A lot of people think about hypersonics when they talk about it in the press, and they use the word hypersonics as if it is a tangible, singular thing, even as definable as GPS or laser. And hypersonic is not a thing, it is a regime, it's a flight regime. And typically, imagine that little blue blob actually belongs in the bottom left corner there. Typically, we operate atmospherically at somewhere less than Mach 5 times the speed of sound, or roughly 3,300 miles an hour, and below 100-kilometer altitude, the edge of the sensible atmosphere. Most aircraft operations, most missile operations, most things that we do commercially or militarily fits in that realm. When we want to go to space, or mostly go to space, we typically stay left of that orange line. We go up at speeds of Mach 3, 4, 5, or so on, and then we're out of the atmosphere. We don't experience the hypersonic environment. And when we want to go really fast, like that Centaur upper stage in the upper right corner there, we end up going way high. We're at 600-kilometer altitude or beyond, because we're on our way to a much higher orbit. The hypersonic regime is inside the orange lines, and typically it's below 100-kilometer altitude and above Mach 5. And from a operational perspective, from a platform perspective, those are things that I think we use the almost exact same picture, Rodney and I, of the X-15, but we're also looking at things like shuttle lived in that space when it came through the air. Re-entry systems, you see a missile warhead representation there. Also the X-51 that I've got a picture of that was designed to live, operate, exist in that domain. And so the environment for hypersonic flight is really bounded by that regime. It is truly an atmospheric event or an atmospheric set of conditions. So what is it? Well, we can think of it in terms of physics and chemistry. We can certainly talk about, if we go back to what we learned about in chemistry, we can learn that's when the perfect gas relationships break down, the assumptions break down. PV is no longer equal to nRT. And we could spend hours or beers talking about that, but those caloric and thermal imperfections have a true impact on what happens to a system, to a vehicle, to an airframe. And just that difference alone is pretty significant, but it's complicated by the fact that you get strong shock waves and high stagnation temperatures, you cut off ramjet test articles, and any number of bad things can happen, or you can exploit them and take advantage of them. So it's a very, very challenging environment, thermally, mechanically, acoustically. Acoustic things happen in the boundary layer and beyond. It's exceptionally acoustically noisy environment. But that's not a bad thing, necessarily. There are profound implications for aeromechanics, things like that. There are also profound implications for the things we want to do with a vehicle. If we're going to put a vehicle over an adversary's battle space, we want to put sensors on it. We want to learn what's going on. We want to extract data. We want to communicate. We want to deploy payloads or employ them in some way. And by the way, if we're thinking about a reusable multi-mission system, we need to be able to maintain it, to operate, to have it logistically supportable. We need people to be able to sustain that thing. So why is this significant? Why do I bother bringing that up to this particular audience? Well, people like Rodney and people throughout this group are busy training folks that do the stuff, tackle the problems on the left, rocket scientists, which is great. We need those. I have 2 Texas A&M grads in my office, which is a relatively small office of about 15 people, and an intern that are working with my wind tunnels, which is really cool. They're incredibly smart kids, and they're accomplishing some really neat work. Thankfully, I've offset them with 3 Boilermakers, so I'm happy. But that right side, the challenge is also there for everybody else in not only the aerospace community, but the engineering community. So we need people who are experts in chemistry, physics, electronics, electromagnetic waveforms, getting that information to and from a platform, taking advantage of it. We need people who are good at human factors and truly understand it, not merely for putting people in a vehicle or in a system if you're taking them across the sky or up to space or back down, but also those that interact with the system that is operating over the horizon at high speed where things are happening at 1 mile a second or 2 miles a second. And you've got to be able to bring all that stuff to a useful point of fruition. We need people who actually can understand ops analysis when you're dealing with things that happen at those speeds. You're approaching the speed of thought. You're really pushing this stuff up there. Manufacturing, I'm going to hit on this point a couple more times. People think about hypersonic systems as being expensive. Truly, in the military environment, when you've got a requirement, what it takes to do that requirement is usually expensive, but it's by definition affordable. When you go to the commercial sector, affordable and expensive take on a different paradigm, different mindset. And frankly, if we're not going to be able to make something practical, supportable, sustainable, you're not going to be able to take advantage of it. Manufacturing is a key part of that. And then the sustainable ops are a key part. So let me go to a different part of why the Air Force is working on this. Why do we care about it? Certainly we want to make high-speed systems for military application. We're taking a stepping-stone approach, a stair-step approach, and we have been for 20 years now since the advent of the high-tech program after the National Aerospace Plane Program. So our successes build upon each other. What I show there is the first generation of practical hypersonic systems that we're pursuing presently through the research programs, through the transition programs. You heard about some of the stuff that AFRL and DARPA are doing together from the Lockheed presentation earlier. So the top picture is the X-51, X-51A specifically. We had 4 successful flights, 3 successful flights, 2.5 successful flights. Can I take that? Which, from a researcher's perspective, is actually pretty good. When I look at all the flights since 2000 in the high-speed regime that the U.S. has accomplished, we're batting over 600. And in pretty much any ball game, that's a good number. But there's still things to learn. So those things to learn are indicated below there. We, as a community, AFRL and our partners, nationally and internationally, have been sponsoring a lot of flight research experiments. Things like high cause, high shot, high fire. And right now, we've had about a dozen of those in the past 12 years. We're not getting quite the ops tempo that we'd really like because the sky is a great place to go learn stuff, which is why things like the Bolt experiment that Rodney talked about are going to be incredibly important. We've got to get out there and learn. That first generation gives us expendable vehicles, relatively small engines, we call them 1X scale, cold structures, aluminum, steel, titanium, Inconel, covered with a thermal protection system that is barely advanced beyond what we use on the shuttle system. It works. And the aerodynamics are kind of okay. They're medium lift to drag. We're not trying to really mitigate all the bad effects of things like boundary layer transition. We're just trying to accommodate them. You go on to the next step. So if the first phase is the S&T that'll be ready by 2020 and is being developed and validated right now, the next phase is what we're doing as a community before 2030. It's getting into that first generation of truly reusable systems. Things that if you want to think about it one way, it's like a hypersonic Predator or Reaper. Something where you've got larger scale, and we're developing the engines right now in a program at Arnold Air Force Base and Wright-Patterson Air Force Base. Engines that are fighter engine scale in size, so 1 to 2 feet in diameter, which for a scramjet is an incredibly big engine. Lightweight, warm, and hot structures. You've got to be able to build these things so that they last longer, fly longer, and have a good chance of holding the shape to within the tolerances you need. The definition of holding tolerances might change a bit, though. And higher lift to drag aerodynamics. The picture I've got there is intentionally not something that looks like a really big SR-71. It's a different way of thinking about how do you take advantage of the high speed. And you may have a multi-stage system to go accomplish military missions as well as commercial missions. What about the future? Now we get the things that look like what people have been thinking about for high-speed systems for a long time. Rocket-powered or scramjet-powered or combined cycle systems, large engines, engines that eat 1,000 pounds of air a second or more. That's pretty big. That's getting you in the class that lets you launch payloads of 20,000, 30,000 pounds. Hot and hybrid structures, a truly hot structure that can be reused over and over and over, 250 missions, 1,000 missions. Advanced aerodynamics and controls, the things that you need to make something that doesn't have gaps and seals. It's taking advantage of novel effectors, phenomenological effectors, plasmas and fluidics and the like. Because all those other things, seals, gaps, et cetera, make it hard to maintain a system. So that's our target for about the 2040 timeframe. It's really easy to say, what's hypersonics good for if we progress down that stair step? The set of arrows on the right side of the page are the traditional way of thinking, hey, if I go faster, I get there sooner. If I go Mach 10, I get there 10 times faster than I do go Mach 1. Okay, great. And that's that first bullet is increased range time. From a military operational standpoint, it means I can cover 100 times the area from a single point within the same time that I could before. And when you think about how we tend to operate, for example, over in Afghanistan and places like that, we tend to put an aircraft on orbit, it sits there, and it dominates a battle space, which is actually a very useful military mission. But when you add energy into a system, you add speed, you also increase lethality, you reduce its vulnerability, you reduce its flight path predictability if you're dealing with a major peer who also has really smart systems. That per system cost isn't going to go up because the per system complexity is going to go up. But when you throw all these things together and you then try to accomplish a militarily useful mission, you use a lot fewer systems and the overall mission cost can go down. That's one of the reasons the Air Force cares about this stuff for aircraft and missiles. Another reason we care about it is for space access. And I've drawn an example from a study we did back a few years ago, put in the Journal of Propulsion, Journal of Spacecraft and Rocketry. You typically think about going to space, air-breathing hypersonics, or putting air somewhere in the system lets you improve your payload fraction, payload mass fraction. And you can draw lines and say, yep, it's smaller on the ground, it's easier to put payloads into the vehicle, a smaller footprint. I might actually be able to tow it into a standard hangar. I can do that horizontal takeoff, horizontal landing thing. But what does it really mean if I want to operate it for something other than a military mission? Being able to put something up in space really quick is nice when you're responding to a threat. For the rest of the world, for the rest of the operators, the commercial business, the increased flexibility in ascent and descent may be key. And what we've got on the picture here is a conceptual, the result of using a conceptual vehicle with a fully air-breathing first stage to go to hypersonic speed before letting the second stage go, launching out of the Cape, and going two completely different ways. If you immediately run down range, you intercept a trajectory overhead or pick your trajectory on the far upper right end there. If you go follow that yellow line and go back around the other way, take a big swing out over the Gulf and go back, you can pick that trajectory up actually 8.5 minutes earlier. And by the way, that entire envelope is drawn as a whole bunch of different points you can hit from pick your launch time, where you want to go, what your azimuth is. And that's a flexibility aspect that we started looking at very seriously. Why do you want to take advantage of this stuff? Well, it lets you do the mission better, smarter, differently. If you go to a high-speed air-breathing system and a rocket system, because you need rockets to finish your trip to space, you can reduce your total stage count from 4 to 3 or 3 to 2. But each stage gets more complex. Part of our challenge within the laboratory is to reduce that complexity. Why is this important to the folks here? You educate our workforce, a lot of you. As I mentioned, we've got a couple of Rodney students. I've got students who also have done undergrad work here and gone up, or young folks who've done undergrad work here and gone up to other schools for their graduate degrees. And we typically look at what can we do. The listing of different projects and sponsorships that Rodney showed was perfect because it showed a lot of places where we typically spin on knowledge in aerodynamics, aerothermodynamics, propulsion, control, high temperature structures. What can you get out of it? Aside from the fact that you're getting, you've got sponsors for projects between AFRL and AFOSR, you ought to be able to get spin-off. You ought to be able to look ahead at that next generation beyond what we saw today from Boeing and SpaceX at future systems. How can they do their mission better, faster, smarter? How can they more efficiently, more effectively put stuff up in space, bring it back? And there's people out there looking at point-to-point transport at high speed. I'd love to have a ride in a ultra-fast jet to get from here to wherever I'm going. I'm still gonna have to wait for my bags at the other end, but I don't know that it's really practical for point-to-point transportation of humans. But even so, take a look, watch for the opportunities. We've got a lot of work coming on within the Air Force. AFRL is developing hypersonic technologies for military applications, working with Lockheed Martin, working with Texas A&M, working with UT Austin and Arlington. We are solving a lot of tough technical challenges that make this stuff practical. And so the institutions here are critical to us helping making this extraordinary thing we call hypersonics routine in the relatively near future. Thank you.
Thank you, Glenn.